Most people think AI is all about data. The more data you give it, the smarter it becomes. More images, more text, more examples. The assumption seems obvious, but that's not the whole story. The most powerful AI systems learn the structure behind the data. Structure means the rules that generate the data, the patterns that cannot appear by chance, and once you see this, you start noticing it everywhere. Today, AI is making breakthroughs across many domains. Image recognition, superhuman game playing, protein structure prediction, physics simulations. And behind many of these breakthroughs is the same principle combining data with the structure of the domain. Take image recognition as an example. Over the past decade, image recognition has improved dramatically. Today it powers many systems we use in everyday life. Face recognition on smartphones, object detection in cameras, medical image analysis. Explaining all the details would take us too far, so let's focus on one key idea. At first glance, an image may seem like nothing more than a grid of pixels. But if AI had to learn from raw pixels alone, without any assumption about structure, the task would be much harder. Because meaning in an image does not come from isolated pixels. It comes from how pixels relate to each other. Nearby pixels are connected. Edges emerge from local contrast. Shapes emerge from edges, and objects emerge from shapes. That is the structure of images. And this is why convolutional neural networks were such an important breakthrough. They are designed to exploit this spatial structure. So envision, progress did not come from data alone. It came from combining data with the spatial structure of images. The same principle goes beyond images. Let us look at a game. In 2016, DeepMind's AlphaGo defeated the world champion Lee Sedol at the game of Go. This was not supposed to be possible. The board has 19 by 19 squares. The number of possible games is larger than the number of atoms in the observable universe. Searching through all of them is not an option. AlphaGo did not win by searching harder. It won by learning structure. Go has spatial structure. A pattern in one corner of the board means something, and that same pattern means the same thing wherever it appears. This is exactly the kind of structure that convolutional neural networks are built to capture. AlphaGo also learned a second kind of structure, the structure of decisions over time. Each move leads to a new situation, and consequences unfold many steps later. This is captured by reinforcement learning. Data alone could not have solved Go. The space of possible games is essentially infinite. What made AlphaGo work was the decision to encode what we already know about the domain, spatial locality, sequential reasoning. Structure is not a cage. It is a foundation. The same principle appears again in a completely different domain. Not games, not images. Biology. For 50 years, one of the hardest problems in science was protein folding. A protein is a chain of amino acids. The shape that chain folds into determines everything: how a drug binds, whether a disease can be treated. The challenge, from a sequence of amino acids alone, predict the three-dimensional shape. Then in 2020, DeepMind's AlphaFold solved it. Not by simulating every possible fold, by learning the structure of the problem. Proteins have structure. Amino acids close in the chain tend to interact. Certain sequence patterns predict certain shape patterns. These relationships follow rules that can be learned. AlphaFold encoded this knowledge directly into its architecture. It modeled which parts of the sequence influence each other. It incorporated known physical and evolutionary constraints. It did not treat the problem as a black box. It brought in what we already know about how proteins work. The result was atomic-level accuracy. A problem that had resisted 50 years of scientific effort, solved. The data existed for decades. What changed was how that data was combined with the structure of the domain. And this same principle appears one more time in physics. In physics, we do not just have data, we have something stronger, we have laws. The equations that describe how fluids move, how heat spreads, how waves travel. These were not discovered from data. They were derived from first principles, tested over centuries, and written down exactly. So here's the question. If a neural network is trying to learn how a physical system behaves, why would we ignore what we already know? A standard neural network fits the data points, but fitting the data is all it can do. Where observations exist, the model performs well. It learns the pattern and follows it closely. But in the real world, data is rarely complete. Sensors have gaps. Measurements are expensive. Some regions of time or space are simply hard to observe. And in those regions, the standard neural network has nothing to hold on to. The curve becomes unstable. It has no way of knowing what the right answer is. This is not a problem you can solve by training longer or using a better architecture. The network simply does not know the rules. It has never been told how the system actually behaves. Physics-informed neural networks, or PINNs, take a different approach. The name says it all. These are neural networks that have been informed by physics. The governing equations are not treated as an external constraint. They are built directly into the training process. Instead of training on data alone, the model is trained to satisfy two conditions simultaneously. First, fit the observations. Second, respect the governing equations. These two requirements are combined into a single loss function. Data loss and physics loss optimize together. And the difference is clear. The standard neural network stays close to the data it has seen. But where data runs out, it drifts. PINN is different. Even in regions with no observations, it knows the rules. It follows the physics. The prediction remains accurate, not because it has seen more data, but because it understands the structure. That is the key insight. Data tells the model what happened here. Physics tells the model what must happen everywhere. And when you combine the two, the model can predict with confidence even where no data exists. So let us take a step back. We started with images. We saw how convolutional neural networks exploit the spatial structure of pixels to recognize objects with remarkable accuracy. We moved to games. We saw how AlphaGo combined spatial structure with sequential reasoning to master Go, a game that brute force could never solve. We looked at biology. We saw how AlphaFold encoded the physical and evolutionary structure of proteins to crack a problem that had resisted 50 years of effort. And we touched on physics, where the structure is not just useful, it is exact. The laws are already written down. And physics-informed neural networks build those laws directly into the learning process. 4 completely different domains. The same underlying idea. The most powerful AI systems are not the ones trained on the most data. They are the ones designed to understand the structure of their domain. Data tells you what happened. Structure tells you why. And when you combine the two, that is when breakthroughs happen. If this way of thinking about AI is new to you, I hope it changes how you see the field, because the next wave of AI breakthroughs will not come from bigger data sets alone. They will come from better structure, and that structure is already all around us, waiting to be encoded